Hello again, Dan Olds, doing another webcast that's geared towards helping student cluster competition folks compete a bit better, but also towards you in the general IT, HPC IT, whatever sort of IT you're involved in, do a little bit better job. And I have a really interesting topic today. We're going to talk all about liquid cooling and talk with the folks from Cool IT Systems who have really come on in the last several years in pioneering this whole move back to the future with moving back to liquid cooling. And with us today, we've got Patrick McGinn. Did I pronounce that this time correctly, Pat?
You nailed it.
I nailed it. Excellent. I will never use
Nailed
that
it.
again. I'm just going to go ahead and not use your last name because I know I pronounced it incorrectly the first time we talked. But tell us a
That's no
little bit
problem.
about yourself.
Sure. Well, thanks for having me, Dan. As you said, my name is Pat McGinn. I'm the product manager for our Rack DCLC program at Cool IT. Rack DCLC is really our rack-based data center cooling systems that mostly tie into data center infrastructure. Cool IT has been in the liquid cooling market for 13, 14 years now. We have a pretty strong IP portfolio, about 45 issued patents, and there are roughly, I think, 19 patents pending, so it's been a very busy past few years for us. As you mentioned, we've really come on, as you put it, in the past 2 years. We've made a big transition from the desktop market into the data center market, and it's been a really good showing for our company so far. We've had really solid growth. We've managed to innovate quite a bit in the space, and really excited to be living,
Yeah.
in the high performance compute space.
Well,
It's a fun time.
you're in the right place at the right time, and one of the reasons that we're talking to you is that you guys supported the Edinburgh Student Cluster Competition team at ISC 14, the team that set first of all, they were the first team to get over 10 teraflops LINPACK in under 3,000 kW, and that record still stands today.
That's right. That's right. They did a really good job. So, we didn't do it all for them. We provided them with some of the tools, and they really did some great work. We can talk a little bit about how they did it, I think,
Sure.
in today's presentation.
But it's something that the other student cluster competition teams ought to investigate, and certainly something that will pay off in data centers too. But let's take a few steps back, and let's talk a little bit about why the main broad reasons why customers are moving back to liquid cooling.
Sure. I think that there's several different reasons, of course, and there's different drivers for each subset of customers. I think that one of the most important things to understand is just really the power of, the cost of power these days. Data centers use, in North America, 3% of the entire energy grid. That's about 2% worldwide. So they really do use an immense amount of power to drive the IT, and it's quite expensive. So the harder you can drive efficiencies, really the better the benefit to your operating expenses.
Sure.
And that, from a very high level, is what drives this conversation.
Sure. So it's efficiency, but there's some other things that come out of that. Smaller footprint for systems because you can get higher
Absolutely.
density.
Yeah, absolutely. When you increase densities, you need less of everything. You need less land, less building, less shared infrastructure, less racks, less
Less
switching.
cables, everything.
So you can really, exactly, you can pare a lot of stuff down. Data centers are not your average building. Of course, there's a lot of very expensive, very specialized components that go into data centers. So the more you can reduce those types of specialized components, of course, the better off your initial capital outlay is
Sure.
going to be.
And plus, there's a performance aspect to this too. That if you keep um, components cooler, they tend to operate a lot better.
That's exactly it. So there's reliability benefits. There are certainly efficiency benefits inside the server as well. If we look back to the team from Edinburgh who competed last year at ISC, they were able to completely remove, if not unplug, a lot of the fans that were operating inside the server. That allowed them to dedicate more power to their effort, essentially. There's also leakage current. When you run the components cooler,
Sure.
You will see about a 10 to 12% efficiency gain just at the server level itself.
And that's without any sort of overclocking or anything like that. Just more efficiency from less leakage, current leakage?
That's just running the components cooler. So if you run those things, typically they run up towards 70 degrees Celsius. We'd be running them closer to 40 or 50 degrees Celsius. They just run cleaner.
And the other teams that have tried liquid cooling, including Edinburgh, they've also noted that they've been able to run at higher frequencies, in turbo mode longer, and I think we're going to start to see some teams really try and take advantage of that with liquid cooling.
Absolutely. And it's I guess where we got our start. As I noted, we lived in the desktop market for some time. So I think the number one place you'll find our desktop coolers is in gaming equipment. That said, in a lot of high performance workstations and high frequency trading machines, on Wall Street you see a lot of liquid cooling. There's quite a few ways that guys will use hardware acceleration to benefit them.
Sure. I've done a bit of that myself. At least, and it's also nice from an environmental standpoint, less heat in the room, less noise. It's a good thing all the way around. But there's different ways to do it. Let's talk a little bit about the choices in liquid cooling these days. I guess starting from the least efficient to the more efficient, one of the things that I see from data center vendors are like rear door chillers that have a radiator in the rear door. They're getting the heat pushed into the radiator, then expelled from the room that way.
That's it. Yeah. The rear door heat exchangers come in a number of different flavors, and they're really popular right now. They have the major benefit, of course, of 100% load capture. They're room neutral. So what that means is any and all heat produced by the servers is pushed out through a chilled coil, and that coil transfers that energy into the water right there at the door. So these are used a lot because they can basically strap onto or be connected to any rack. They just need an adapter plate. They can tap into the existing chilled water supply that is usually in place already for the crack systems. So they're an easy retrofit to manage hot spots in an aisle, to manage your maybe one or two higher density racks that you might have, and they're not all that expensive. They can be integrated fairly easily.
Yeah, it's a good choice these days for sort of getting your feet wet, so to speak, in liquid cooling.
That's it. It's sort of a gateway drug. Guys some people are a little nervous to bring their liquid into the server. We've been dealing with that sort of challenge called barrier to entry for some time. Other people think it's completely fine.
Yeah, and I think that the market is coming around. I know that from my experience with running a couple of fairly large workstations, liquid cooled, I've never had the hint of a leak anywhere, and that's with essentially homemade stuff. I know that your things are a lot more sophisticated, and actually let's talk about that talk about the next method, which is direct contact. And my understanding of this is where you have a cold plate that has liquid circulating through it, directly connected to the components, CPUs, memory, GPUs, what have you.
Yeah, that's exactly it. So what I usually highlight here is that it's a very safe and reliable way to remove a very high percentage of the heat. So we remove the heat off of, obviously, the components that we position cold plates over. That's typically CPU and GPU, though it can be memory as well, maybe VR, and custom FPGA, ASIC, that sort of thing. It's been done for quite a long time. Fujitsu and IBM have been doing this their own way for a while. We really changed things by bringing in a vendor agnostic system. So if you wanted liquid cooling before, you had to buy Fujitsu, you had to buy IBM. With us, you can buy our systems. We have a bunch of different types of components that we build that can be fitted together to fit inside a Dell, HP, Supermicro, Cisco, what have you. So I think a lot of our recent success has been due to our flexibility in terms of what we can put cold plates on, really. But there's quite a few players in this space.
Sure.
It really is a nice tie-in to existing servers, so you don't have to go and change your server architecture all that much or at all, or with some of the other technologies you may need to.
Sure. And the particular type of product that they're buying from you, that's less dependent on the server vendor and probably more dependent on the socket or particular CPU that they're trying to cool, right?
Yeah, that's it. And we produce cold plates for all popular CPUs and GPUs on the market. So, we're yet to find in our transfer to the data center a server product that we can't cool.
Yeah. Well, that's the thing is that they're standardized at that level, at the
That's right.
motherboard level. That if a two-way is using particular Intel E5 socket, then those holes where you're attaching the cold plate, they're going to be in the same place on every server
That's
because
exactly it.
you fit on just like a heat sink.
That's exactly it. We take up less space than a heatsink. So
Yes.
we're passively cooled, where we use a centralized pumping system. So the pumping comes from the heat exchanger. And it's the heat exchanger in this cold plate space with all the different vendors that you really see the differences. So we produce a number of different types of heat exchangers. For example, we have heat exchangers for people who can't bring facility water to the aisle, to the rack, to the computer. We use our AHX product. That sort of gives you the race car effect, where it's still exhausting the load out into the data center, but it really allows you to exercise liquid cooling for the performance benefits and the density benefits, just not the efficiency benefit.
Okay. And when you're talking about the rest of the components, do you guys also have heat sinks for memory? I think you mentioned that you
Excuse
did.
me. Yeah, we do. We produce memory. What people usually figure out pretty quick is that even though it's fairly easily done in terms of cooling the memory, that because they don't produce much heat, the cost benefit is not as strong. So your dollars per watt, for example, that you're picking up is quite a bit higher. You spend more money to pick up a
To get that
smaller amount of power.
incremental improvement.
Yeah,
So the
that's
real
it. So there's
so the real big performance here, big bang for your buck, is in cooling CPUs and GPUs then.
you got it. That's exactly it.
And you guys, I'm sure you do. You have cold plates for the passively cooled GPUs, but do you also have them for the full size cards?
Yeah, absolutely. Yeah, absolutely. We
Good.
work pretty close with all processor manufacturers to design the systems for all of their popular cards. So all of the Intel co-processor lines, the NVIDIA, K20 all the way to current K80 stuff. We to be competitive in the market, we have to be
Sure.
to have cold plates for each piece.
And how much cost does this add? Just sort of a ballpark. I'm sure it's different in every situation.
Yeah, sure. So it depends. If we look at a standard one-use server, our kit per server is somewhere in the neighborhood of $90 to $100 typically.
Okay, so per server, and then the cost would be of the heat exchanger would be amortized over how many servers you connect to it, of course.
Exactly. Yeah, and we have a number of different heat exchangers that work dependent on if it's a low volume cluster of a few racks. We have rack-based heat exchangers, but then if you go to an entire aisle or row, we would have a larger heat exchanger that would serve those pieces. So cost in that area really does depend on which heat exchanger you select.
Well, let's talk a little bit about the other ways of doing it. One of the things that always gathers a lot of attention, and we're seeing more and more examples of it, are the various immersion type cooling systems, where essentially you're dipping an entire server, entire rack into some sort of liquid substance that steams and bubbles and boils. And you pointed out in your slides that will show up here on the screen that there's a couple of different flavors of this. So let's talk about single
Yeah, there are.
phase first.
Yeah, sure. So there's at least two, a single phase and two phase. Single phase is quite a bit further along than two phase, I would say, in terms of it being an available product on the market. Single phase is characterized by keeping the fluid in a liquid phase at all times. It has the obvious benefit of 100% load capture. Some of the challenges to immersion are that you need to change out all of your spinning disk drives to solid state drives, to SSDs, and you need to relocate any optical connections outside of the rack. But in terms of being a sexy solution and getting lots of press, it's certainly done well over the past little while.
Well,
And you can do it a number of different ways.
The things that I've seen of this in use, and it's at a couple of student cluster competitions, been using the mineral oil stuff, and that's pretty messy, fairly. I mean, it's not harmful, it's not nasty stuff, but it's not trivial when you start swapping equipment in and out of it.
No, it's not.
I've got some videos up online. I'll show some links, throw some links in on those. But it's, if you're doing a lot of equipment in and out on it, it can get pretty nasty.
I haven't been there for it, but certainly it would change the procedures that IT people would use around their equipment. You definitely can't just pull the server out and begin working on it again. It would need some time to drip dry, I guess.
Yeah.
And I think there's some new and different processes that might be challenging.
Yeah, the mineral oil is pretty persistent on the equipment, and that's one advantage of at least the 3M stuff that we talk about in two-phase immersion, is that once it comes out of that bath, it's pretty much dry and you can just start working on it.
That's right. It's a pretty cool solution as well. Again, two-phase immersion, we don't see very many products out there that use it. In alternative markets, Bitcoin, for example, there was one group who were very successful with it. They've since been bought out. But really, I think what we need to note here is that for those who aren't familiar with it, is that it uses a phase change to exhaust the heat. So essentially, it uses a liquid with a very low boiling point. It boils the water off into a condenser that sits above, and then it drips that liquid back into the tank. So it involves a little bit of an alternative setup.
It's
and
pretty
maybe that's why
exotic.
it's taken.
Yeah.
Yeah, it is. It's pretty neat, though. 3M has done a good job of pushing the conversation on two-phase immersion. There's another group named Solvit who also have tools that they're trying to push into the market. So, we're keeping a close eye on two-phase immersion.
Sure.
It certainly has some benefits, and it'll probably show itself pretty well in the next few years.
Not inexpensive these days either.
No, the solutions as they are today, probably because they're not really manufactured in that great a volume, or can be quite expensive. I guess it depends exactly which one you pick, but
Well, and it's pretty exotic fluid that they're using too.
That's right, exactly.
Well, let's talk a little bit, coming back to direct contact. On your cold plates, how difficult is it to get at a component and replace it?
It's really simple in our stuff. We put a lot of time into the original design, and the design theory is such that the same people that are typically walking down the aisle and replacing CPUs and working on memory should be able to work with our systems. So again, most of our components come from the desktop world, the same types of components where people are installing them themselves. So a CPU, for example, you would just take our passive cold plate off, just like you would take a heatsink off. No difference really. You would replace the processor, put some thermal interface down, just exactly like a heatsink, and then screw it back down exactly like a heatsink. So it's really simple in terms of the procedures that one would need to go through to complete service on the server.
Okay, so there's must be a liquid quick disconnect near that cold plate.
That's exactly it. Yeah, yeah. Each server is connected to a rack-based manifold. That sort of racks just like a PDU, typically at the back of the rack. And if you want to work on that server, you would unplug the power like you usually would, and you'd reach over just a few feet away, and you would unplug the liquid circuit, and then you can pull that server out, and you can work on it as per your normal procedures.
And so there's no draining, there's none of that type of thing. Those quick disconnects hold the
No.
liquid in the lines.
The customer never sees the liquid. We have tens of thousands of systems all around the world that get shipped inside different servers from their manufacturer. And I would bet actually in those closed loop systems that a lot of the people in the data center don't actually know the liquid's there. It's quite discreet.
Excellent. Well, this is a really great overview of the technology. Let's delve a little bit deeper into how it can pay off for the performance-oriented among us. And one of the pictures that really caught my attention in your slide deck is the power of H2O, that the cooling power in a glass of water is equivalent to a room full of air. That's a really interesting way to illustrate that.
It is, and it's sometimes hard for us to change the minds of people who have been working in the computer data center industry for years. And I think this slide is really interesting. What we're showing here is just that water does a much better job of absorbing heat. Air is pretty tricky to use to cool. It's not all that good to use for cool. It is safe though, and that's why it's been used for a long time. So the power it takes to first chill water, and then bring that chilled water to a coil to chill the air, and then try and effectively move that air down an aisle to the right spot, and then get it up to the right server. It takes a lot of power to do that.
And to make sure that cool air hits all the nooks and crannies that are producing heat inside that server as well.
That's right. It's very difficult. You have to start at the very beginning with chilled water, which takes quite a bit of electricity to get cold to begin with. What we suggest instead is to not worry about chilling that water, to keep it in as warm water, ASHRAE W3 to W4 standards, and to bring that water directly to the chip. It's a lot easier to control.
Let's back up just a second. When you're talking about warm water, how warm water are we talking about?
Generally, the temperatures we deal with are about 30 degrees and higher, 30 degrees Celsius and higher. So it's quite warm. That type of water can be made almost all year round in most regions with passive cooling structures, so with dry coolers or cooling towers. So it really reduces, and a lot of the time eliminates, the need to use a chiller, which of course is it.
And 30°C is quite high. I mean, for those of us that are Fahrenheit oriented, that's 86 degrees Fahrenheit.
That's right, and we'll often work up past 100 degrees Fahrenheit. 30 degrees seems to be what people ask us about. But we've worked as high as 40, 45 before. So it really is warm water cooling.
And so for most, just being able to expel this into the ambient air outside is enough of a heat loss in order to be able to provide water below that temperature back into the system.
Exactly. The primary cooling device, the facilities device that they need to cool that water is a lot easier and more cost effective to operate when you need it to produce warm water.
Very cool stuff. Now, when we're talking about cooling for performance, we definitely see you're looking for performance per watt, and definitely an advantage to reduce the server fan count, which is, I mean, you can essentially eliminate all of them, right?
Which cooling technology you use, yeah. You can potentially.
You're gonna need some air probably to go in to cool the memory if you're not going to go that far. A little bit for the ASICs on the motherboard, but that's not a whole hell of a lot. So you guys figure, I think, what, about a 3/4 reduction in fans?
That's usually it. If you put GPUs in the mix, typically it's closer to 80. But that's it. It's usually between 65-75% of the energy is going to be evacuated through the warm water.
Okay. And being able to do that, so you're obviously going to get more efficient on the power, but how much more performance can someone get out of these systems with having a thermal envelope that's then now that much bigger?
Sure, sure. So we have customers who use liquid cooling to safely overclock into the maybe 5 gigahertz range. There's a lot of secret sauce that goes into being able to do that,
Sure.
not just the liquid cooling. Um, and they hold those secrets pretty closely.
Oh yeah,
But
that's
people will.
competitive advantage.
That's exactly it, and they use it for lots of different industries. There's high frequency trading industries. There's CFD and design industries that will use that. There's a lot of groups that typically will pay a per core licensing fee. So the more they can get done with that core, the better off their business is really at the end of the day.
Well, I hadn't really thought about that for a way to maximize what you're paying for ISVs.
That's exactly it.
That's a pretty big opportunity, I would imagine. Now,
It is. It saves people a lot of money for a pretty fairly small initial cost.
and I know that this is just coming from, anecdotal. I don't think there have been any studies on this. But when you keep a component cool, well within its specifications, or even lower than what it's than near the upper limit of its specifications, and even though you're overclocking it, have you heard or seen anything that says that the life of those components is shortened at all?
You know, we generally don't comment on that.
Yeah,
We let Intel and AMD and NVIDIA and the rest of the processor manufacturer gangs comment on that.
sure.
What we were talking about earlier is running the parts more reliably, and liquid cooling does do that. So typically with rack DCLC, we will keep, even with warm water, 30 degrees Celsius water, you're saying 87 degree Fahrenheit water, we'll still keep that part somewhere down around 40 degrees Celsius. So it really is running it in a range it's not used to running it, right? And the increased reliability from that is significant.
Gotcha. And I understand why you can't comment on that. Again, there's hasn't been, at least that I've seen, many good studies done of what the lifespan is and how it can be affected. I know that in the past, overclocking and pushing systems too far, a lot of horror stories out there, mostly, I mean, anecdotal about blowing up processors and things like that. But those were in the days before many people had tried it, and people moving too fast, too quick, moving too far, too fast is probably the best way to put it, in trying to eke out as much as they can out of these components. But the real reason behind, I think, a lot of those early failures is that they couldn't control that temperature, that heat, and get the heat out of the system quickly enough.
Yeah, that would be your first call. And I think when you're dealing with hardware acceleration, you really need to know what you're about. You need to understand what exactly you're putting the processor through, and you need to understand what your new potential range of performance might be with the liquid cooler.
Sure, and to test, and to go slow,
That's right.
go
Move slowly.
move very slowly. There's a lot of information out there on how to do this, but move very slowly and test constantly. And but I think that there's an awful lot of performance that folks are leaving on the table by not exploring this.
Absolutely, absolutely. If you're looking at the type of competitions we do at ISC and supercomputing in the U.S., these types of competitions are prime candidates for liquid cooling.
Excellent. And you guys have relationships with most of the vendors, right?
Server vendors or which
Server
vendors?
vendors.
Yeah, we do. We have good working relationships with these different groups, at different levels.
Sure.
Most computer groups, of course, work in the desktop and server space.
But would you say the reason I'm asking that is that if a student cluster competition team who's sponsored by a particular vendor, if they were to go to that vendor and say, "Hey, we want to liquid cool this," and then push it a little harder, the vendor is not going to faint from the shock or decide that this is just way too out there. I mean, the vendors are a lot more friendly to this than they have been in the past. I guess is
They
my point.
are, yes, that's right. So we would invite all the student cluster teams to discuss that with their partner, and if they need a hand in that conversation, we're always available.
Absolutely, and they can get to you guys through me. I'll throw some contact information up there. And this has been a great conversation, Pat. Really appreciate it.
Yeah, no problem. Thanks, Dan. Thanks for having me on.
And we will talk to you soon.
You bet. Thanks again.